We're looking at problem number 7 on review 8. And in this problem, we're given the graph of the derivative function and asked some questions about it. And the first question we're asked is, on what intervals is f, the original function, increasing? And so our answer in this case for A is going to be, well, the original function is increasing as long as the derivative is positive. So the derivative is positive here and here only, which means that it would be on the interval from -3 to -2. Everywhere else the function is either decreasing or not changing. Part B says, find the x-coordinate of each point of inflection of the original function. So what we want to keep in mind here is that points of inflection occur when the original function is increasing or decreasing most quickly. So if you imagine we've got some function, I don't know what it looks like, but maybe something like this. See that point right there, that point of inflection, is where the derivative is greatest. So we're looking for maximums on the derivative, or we could also be looking for minimums on the derivative. See that right here, that slope right there is the most negative, so that's where the derivative would be at a minimum. So we look at this graph at 0 and at 2, we have maximums or minimums of the derivative function. Therefore, those are going to be our points of inflection of the original function. And there's the bell. You're dismissed. Take a look at C. C says, find an equation for the tangent line to the graph of f at the point 0, 3. Now, in order to write the equation for a tangent, you need a slope and you need a point. The point is right here. The slope we're going to get from this graph. Now, keep in mind that this is not the original function. And a lot of students say that that tangent line doesn't exist because they see the cusp here at 0. However, keep in mind that this is the derivative. So that point right there is saying that f prime of 0 is equal to 2. Did I say 2? I meant -2. So our slope is going to be -2. Our point is going to be 0, 3. Therefore, our tangent will be y equals -2x plus 3. Next part, part D, says here's the derivative function. We want the area under the curve from -3 to 4. So we come over here to the graph and we say, well, this area would be 0.5. I'm using triangle formulas. This area would be -2. This area right here is a little bit trickier. What you have to do is take the fact that you've got this square here. And that square has an area of 4. And then you've got this region right here, which would have an area of, let's see, 1/4 of a circle. This circle has a radius of 2, so that would be 1/4 of pi times 2 squared, which is just equal to pi. So this region right here, its raw area would be 4 minus pi, but I'm going to write it as pi minus 4. And the reason is because it's under the x-axis, which means it's negative. So this area right here is also going to be pi minus 4. The answer to this problem ends up being 0.5 plus -2 plus pi minus 4 plus pi minus 4, which comes out to be -9.5 plus 2 pi. Bringing us to the last problem. Oh, this is a tricky one. See, on the last one, we've got two functions. The first thing I'm going to do is I'm going to break it up into two separate functions. The second thing I'm going to do is I'm going to notice that the endpoints are backwards. And so we want to set those right before we do any calculations. When we take those endpoints and we reverse them, it changes the sign. Same here, so it'll go from negative to positive. This one we're going to use the fundamental theorem. So we've got -2x from 0 to negative 3, plus right here we've got the area under the curve from negative 3 to 0, which would be 0.5 plus negative 2. When you calculate all that out, you end up with negative 7.5.